Hi, everybody. Hopefully your afternoon is going well. We are going to continue with Chapter 5, specifically those problems that we left off on Tuesday. Here they are. We're going to draw these Lewis structures real quick, and we're going to predict the Vesper and molecular geometry of the structures in question. So let me hit this button here. There's our molecules at the top. Let me make sure I have the right color to draw in. There we go. All right, so let's start with... Oh, hold on. Sorry, I got to move this window so I can see what the problems are. Let's start with ozone. Oh. Sorry, my cursor is all over the place. I got it. Oh, no, I'm just an idiot. I'm using the wrong end of the pen. There we go. Okay. This is ozone. This is the stuff that lightning makes when it strikes and you smell that after lightning rain sort of smell. It's also present in car pollution. Because all you gotta do is take two oxygen molecules and bonk them together and rip one of them apart and combine the rest. And you get ozone. It's also important because it absorbs UV radiation. So having some ozone in the upper atmosphere to protect us from the sun, because the sun wants to kill us, is useful. And I just realized that I'm a little off the screen there. There we go. All right. So there are 3 oxygen atoms, and each oxygen atom gives you 6 valence electrons, so we should all be proficient at counting valence electrons by now. And with ozone, there's really only one way to connect these. You just stick them all together. I made 2 bonds, so that's 4 total electrons used, so 18 minus 4 is 14. And then I'm going to go around the outsides and give everyone an octet, starting on the outside first. So there's 6... There's 12. And then now I have to put the last 2 in the middle. Quick question, and I can't see it because it's behind my window, so hold on. For quiz number 4 specifically, all the questions are credit, no credit. There is no way that I can program the questions to get around that without completely changing the questions and just making them really long. So I am unable to do much about that if the questions specify, like, no partial credit. You do get 2 attempts, though, so make sure that you make the most of them and study up on the questions if you are having trouble with them. Alright, I ran out of electrons. I put everything everywhere. I don't have an octet on the middle right here, so I need to fix that. And the way that I'm going to do that is I'm going to take one of these pairs and bond them over here. And now left oxygen has an octet, right oxygen always had an octet. Now the central atom has an octet. I could have chosen the other side, but it doesn't matter because I could just flip the molecule 180 degrees around. For instance, if this was a plane and I rotated it like this, 180 degrees, then what my molecule would look like would be the other side. Like this. And there you go. So either of those is okay, but as we're going to learn that our molecule written in a straight line isn't exactly the best, because now that we've drawn the Lewis structure and we've satisfied the octet for everything, we need to consider geometry, and we need to consider electron groups for that. So if I circle the regions of electrons around my central atom, which is the one indicated with the arrow, I would see that this is an electron group, and this is an electron group, and this is an electron group. I have 3 electron groups. So that gives me a Vesper geometry of something that has 3 electron groups, and if you know what it is, type it in the chat. What is the Vesper geometry of my molecule? Trigonal. I'm going to assume that you meant to type planar. But that's right. I don't know who Pakar is. That sounds like a name. Trigonal Picard. There we go. All right, and that's correct. No, that's okay. If you're typing on your phone, it might autocorrect or something. And then now what we do, now that we know there's 3 groups, how many of those groups we circled are electron pairs? Well, one of them is a non-bonding pair. And so the molecular geometry for this would be, and you type it in the chat, and I'm probably going to get there before you because it's not a very long word. And you can do either of these, bent or angular, will be accepted. And so if I wanted to draw this correctly, it would look something like this. That electron's a little bit lost, but that's okay. That would be a better representation of it. So there is our ozone. All right. I'm going to skip the process for the next molecule. I'm just going to draw the molecules out to save us some time. So SnCl3- looks like it has 26 electrons, and that's going to end up looking like this. And I know what the answers look like just because I've done this so much, so I know what shape goes with an electron count. So that should be the molecule that you drew. We'll circle its electron groups around the central atom. There are 4 electron groups. So its VSEPR geometry is tetrahedral. And of those 4, 1 is an electron pair. So its molecular geometry is trigonal pyramidal. And then we got this one. I apologize if my electron dots aren't very big or neat. I'm just trying to make them big enough to see. We'll do the same thing. We'll circle the electron groups. There they are, around the central atom. So the VSEPR geometry of this is also tetrahedral. I'm going to run out of space, so I'll just abbreviate. Of those, 2 are electron pairs. And so the molecular geometry for that is bent, not bet. Oh no. Oh, everything's terrible. Hold on. You can't see all the comedy of errors that happen on my screen when I misclick something. I go all over the place. And then finally, carbonate looks like this. And because it's an ion... Oh, I didn't do this for the tin up here. So this is an ion too. I'll do that. This is an ion. We'll do that. And so we'll circle the electron groups around the central atom right there. 1, 2, 3 electron groups. Means that its VSEPR geometry is trigonal planar. And the molecular... Oops, hold on. Of those 3 electron groups, there are no electron pairs on the central atom. And so its molecular geometry will therefore be the same as its VSEPR geometry, trigonal planar. All right, hopefully those are the answers that you got when you did these practice problems on your own. Let me know if you have any questions about them. All right. That's the end of geometry. So your job will be to identify the VSEPR and molecular geometry of the molecule that I give you. I will give you the formula. It will be up to you to draw the Lewis structure and then produce those answers. in the quiz and the exam to follow. And there's the homework practice. So make sure that you have done all of the problems that you need to in order to be successful at this topic. Oops, just in case you didn't get that down. 545 to 558. So the next thing that we're going to do, surprising absolutely no one, also relies on geometry. And we need to be able to draw the shape of the molecule in order to figure out whether the molecule has a specific property to it. And that property is called polarity. And so what we're going to do in this next section is first we got to talk about what polarity is and where it comes from. And then we're going to apply it to molecules, because this is going to be very important when we get to Chapter 7, where Chapter 7 talks about intermolecular forces, which is one of the most important things in this class that you need to know for biology, which you're going to study a lot of when you do cell bio and talk about, like, why do cell membranes work? It's because of intermolecular forces and stuff like that. So here we go. The first thing we're going to talk about is a special property of all atoms. And this property is called electronegativity. And in order to study this, we need to consider the notion of covalent bonds, because we've talked about this right here. Electrons are shared in a covalent bond. And in Chapter 4, we talked about how in an ionic bond, electrons are transferred from one atom to another. Specifically, the metal gives its electrons to the nonmetal. And we've treated these as sort of binary extremes. Either you share your electrons, or you just give them away. But it turns out that there is a region within those two extremes. Maybe the electrons are shared, but only part of the time. Maybe one atom wants to keep the electrons closer to it than its partner, because it has a stronger attraction to those electrons. And so the question comes up, can we share electrons unequally? And it turns out the answer to that is sure. It depends on what's involved in the bond. So let's look at two examples. Here's the first example. I'm going to give you Cl2, and if you draw its Lewis structure, it'll look just like this. And we're going to use this as our template to figure out where the electrons in the middle here are. So here's my electrons in the middle. They're in this bond. Now imagine that each of these atoms was pulling those electrons towards it, because those atoms have a nucleus, and the nucleus attracts electrons towards it. At the same time, the other nucleus attracts the electrons away. So it's kind of like electron tug-of-war. Now, given that these atoms are exactly identical, they're both chlorine, which one will tug the electrons closer to the other? And I just revealed the answer. And what you're probably thinking of is, well, they're both chlorine, they have the same protons, they'll pull exactly the same, and it'll be a tie. And that's correct. If both of the atoms are the same, they pull with equal strength. The electrons are shared exactly the same. And so the electrons would be right in the middle. There would be no distribution of the electrons on one side over the other. Now, what that would look like in an electron cloud diagram is that if I drew a region of electron density, the electron density would be roughly the same shape all over. I wouldn't distort it more towards one side than the other. Oops, I didn't mean to go to the next slide, sorry. Excuse me. But now what we're going to do is we're going to change one of the atoms. Boop, there it goes. Do H and Cl both want electrons equally? And now if this was an ionic compound, you might think of this as, well, okay, which one is more positive and which one's more negative? And you'd probably think, well, Cl, I've seen Cl minus and everything. We haven't really done much with H, though. What does H do? Well, maybe it doesn't really want its electrons. And so what would end up happening is this guy pulls weakly on the electrons, But this one's stronger. We'll do weaker and stronger. And what ends up happening is that the center, where the electrons are, gets moved over. And the electrons tend to be closer to Cl. Something like this. Where I have a smaller region of where electrons would be and near hydrogen, and a larger region near Cl. And this is because Cl pulls the electrons closer to it than H does. Now the electrons are still shared, but they're not shared equally. The electrons are just kind of loaned a little towards H as opposed to stuck in the middle equally between them. It's kind of like if you're sitting at a table across from somebody and you have a bowl of chips and you put the bowl of chips right in front of you and the other person has to reach across the table. Technically, you both have access to the chips, but it's easier for you to have them because they're closer to you. Same thing with the electrons here. We're going to quantify the ability of an atom to pull electrons towards itself as this, electronegativity. If an atom has higher electronegativity, it holds the bowl of chips closer to it, and the other guy has to reach further to grab them. They're shared, but they're shared in quotes. Now, the formal definition of electronegativity is that if an atom has a higher electronegativity, it pulls the electrons through bonds to be closer to itself than its partner. Now, depending on who is bonded with who, this can push the electrons all over the place. We're going to rate every atom on a scale from 0 to 4. 4 is the highest electronegativity. So if you have 4 electronegativity, you just win all the electrons, and the electrons just come swarming to you, and everyone else has to deal with that. They have to reach across to grab them. 0 is the lowest. There is no atom that actually has 0, but there are some atoms that are very close to it. Excuse me. On this chart, on this slide here, is a list of all the electronegativities for all of the atoms, and you do not need to memorize these numbers. What it would help you to remember is where the big numbers where the big numbers are, and where the small numbers are. So the small numbers are at the bottom left of the periodic table, and the biggest numbers are on the top right. The general trend is that as you move left to right across the periodic table, electronegativity increases. If you go down the periodic table, down a group, electronegativity decreases. The premise behind this that we principally care about in this class is the size of the atom. Bigger atoms have the electrons naturally further away. Smaller atoms have the electrons naturally closer to the nucleus, and as things get closer together, they get attracted stronger. Now, it turns out atoms do get smaller as you go left to right. That reason is beyond the scope of this class. It has to do with quantum mechanics and physics, and suffice it to say, you don't need to know all of the details for this. You just need to remember that these trends are summarized as the highest electronegativity is in the top and on the right. And this trend is pretty much constant. There are some exceptions. For instance, in the middle of the periodic table, there's this weird region where these metals have slightly higher electronegativities. And you may have heard these called the noble metals before. And the reason they're called the noble metals is because people that are in nobility like them. People like gold and platinum because they are expensive. And they're expensive not only because they're rare, but because they have special chemical properties to them. They resist chemical corrosion. If you've ever had a silver ring or silverware, like actually made of silver, you'll notice that it kind of tarnishes. Like it gets this black, crusty crap on it. That's silver sulfide, and it's a corrosion product that you have to polish off. So people who have silver oftentimes have to polish the silverware before they actually use it. But if you have things that are made of gold, like gold jewelry doesn't corrode. It just stays gold. It scratches, and that's different, but the gold itself won't actually get crusty crap on it. It just doesn't react with ambient oxygen in the air. And so that is because of electronegativity. When things react, they have to transfer or move electrons around. But if something has a high electronegativity, it doesn't want to do that. It just wants to keep the electrons to itself. And so the metals in the middle that I've circled there with a high electronegativity tends to resist corrosion. And that's kind of neat. So that's a property that we use and take advantage of. That's why we make jewelry out of things like gold and platinum and iridium, and not out of stuff like, say, zinc. Because zinc would just immediately corrode if you dropped it in acid or something like that. Alright, oops. And there's our summary. Electronegativity goes up if you move up and right. It goes down if you move down and left. Now, because all the metals end up on the left side of the periodic table, they have low electronegativity. All the nonmetals are on the right side. They tend to have high electronegativity. If electronegativity differences are too large, then the electrons aren't shared. That would be an example of, say, you were sitting at opposite ends of a very long table, and you put the chips in front of you. Then the other person has to get up and get them. They've essentially given you the chips, and they don't have them anymore. As opposed to sitting across on like a narrow table. If your electronegativity difference is really big, then essentially the electrons get transferred, and you have an ionic bond. So we're going to have a threshold in which ionic bonds form. We're also going to have a threshold in which we'll say that sharing is complete, and if you're in the middle, you have a shift of electrons. And so those numbers are going to be given here. So the way that this works is we're going to look at the numbers that are on this table back here. So here are these numbers, and you're going to have to refer to them, so make sure that you have this page bookmarked in your slides or in your book or whatever. We're going to consider the difference between two atoms in a bond. And we're going to calculate the result. So for example, I could have these two atoms bonded together. What I would do is I'd go look up on the electronegativity table what they are, and then I would figure out the difference between them. The difference is delta electronegativity, or the change in electronegativity. The way you do this is just subtract. 2.5 minus 2.1. And the number you get will be in one of these three regions. You're either going to have 0.4 or less. This is less than 0.4, but 0.4 also counts here. So my slide isn't exactly written right. You're either going to be between 0.4 and 2, or you're going to be higher than 2. And so the terms that we use are shown here. Something that is 0.4 or less is nonpolar covalent. And you know, let me just write over what this says here. So because we want to include 0.4, just because it turns out the CH example that I drew, which is now covered up by the slide here, we actually consider that to be nonpolar. Your textbook has a little bit of a issue with that. All right. So something that is less 0.4 or less is nonpolar covalent. We're going to say that the electron density is essentially equal. If we fall between 0.4 and 2, we're going to say that there is some shift in the electron density towards the more electronegative atom. And then if it's greater than if it is greater than 2.0, then the electrons are essentially completely transferred and we call it ionic. Now there is an exception, and the exception to this is if at any point you have a metal involved, we just call it ionic. Is it 2.0 and higher or 0.4 to 1.9? That actually depends on the textbook that you are looking at. For our purposes, if you get the number 2.0, we're going to call that ionic. So let me just, actually, let's just write that here. In reality, it's not going to matter, because you're not going to have a number that lands on 2.0. I'm going to make it more obvious. I'm going to give you things like 1.6, 0.7, etc. And they'll fall neatly into the middle. The one that is, this is the big exception, is this one right here, 0.4. Because as you can see, CH lands on 0.4, and CH is actually nonpolar. CH is very common, and so that's why we want to make that differentiation. But the other extreme is far less common. All right, so let's assign some electronegativity statements to various bonds. So let's do this one, HF. And so I'm going to write down the numbers for you so that you don't have to, not 40, what am I doing? So you don't have to look these up. And so the difference here ends up being 4.0 minus 2.1 is 1.9. And so that falls between 0.4 and 2. So if we had to call this something, we would call it polar covalent. Now, if something is polar covalent, I'm going to need this space, so I got to erase this. We need to indicate that on the molecule by using a graphical representation, because the electrons are going to be more over here. But me drawing a little blob on the molecule or trying to draw a circle around it isn't the best way to convey that information. It takes time and it's sloppy. So we have a better way. And so here's two ways to do this. And both of these are going to be used in this class and also in biology and beyond. The first way is to draw these symbols. This little squiggly D is the Greek letter delta in lowercase. And what we're going to do is we're going to put either a plus sign or a minus sign next to the atom that gets more or less charge. You can think of this squiggly D as partial charge. So instead of it being ionic, where we would put a whole charge like this, we're going to put the squiggly D to represent that we only have part of a charge. The electrons are just closer to one side than the other, but not completely transferred. So because H is less electronegative, we would put the partial positive on its side, and fluorine is more electronegative, we put the partial minus on its side. The other way to represent this is to use an arrow that looks like this. Oops. And the way that we draw the arrows is that we point at the negative side, and then we put a little plus bar on the side that's positive. Now, both of these work. For today, we're going to be using this method where we use these arrows, because the arrows help us show where the electron density is being shifted to. And when we're going to do that with a bunch of bonds in a molecule, excuse me, when we do that with a bunch of bonds in a molecule, we're going to want to consider all the possibilities of where all the electrons get moved to. All right, so that's how we represent polarity. A molecule is polar if it has a big enough difference in electronegativity, and that results in electrons being shifted towards one atom over the other within a bond. All right. Any questions? Let me know in the chat. Because the next section that we're going to do involves us doing this multiple times within a molecule and seeing the effect of that. And this is described in the lab lecture that I prepared for you that you saw last night. So this will show you how to determine if a molecule is polar or nonpolar. So our next objective is to take that principle. We're going to draw arrows for each bond after we figure out whether it's polar or nonpolar. And then we're going to draw all of the possible polarity arrows for a molecule by looking at all the bonds. So the first thing to do is use the arrow notation to do each bond. Once you've done that, we're going to use the arrows, and we're going to see if they cancel each other. And you can think of this as sort of taking my arrows and trying to add them together. If you could add arrows. For example, if I had this arrow, and I added it to this arrow, these point against each other. And so, if I tried to add them together, they would cancel. But if I added this arrow and this arrow, these don't cancel. So I'd go up and then I would go left. And so my end result would be that. And I'm going to show you a graphical way to do this using animations on my next few slides. So if that's like, holy crap, I didn't think we were going to add arrows today or ever, don't worry, I'll show you more examples. Now, if all of the arrows cancel out on your molecule, what that means is that the electrons follow the arrows. And if they go in one direction and then get tugged right back, the electron density returns to where it started, and it's not distributed, and therefore the molecule is nonpolar. But if the arrows don't cancel each other, then the electrons got moved through the molecule in one direction, and thus the molecule is polar. So let's look at an example like this. So here's CO2, and hopefully it's not going to trigger the animation when I start drawing. I'm going to write down the electronegativity numbers, and I have these memorized, so you don't have to worry about them. And let's figure out delta En for each bond. Now it's going to be the same, because I'm always going to be looking at 3.5 and 2.5. So delta En is the bigger number minus the smaller number. That's not the smaller number, that's the answer. And so because it's 1.0, we point the arrow towards the more electronegative atom. So I have an arrow pointing towards O, going to the right, and an arrow pointing towards O, going to the left. So I now have a polar arrow for each bond. And now what I want to do is I want to sum them together. So I have this arrow and this arrow. And what will the result be when I combine those two arrows? Type what you think in the chat, polar or nonpolar. Any idea? Nonpolar is right, because the left arrow and the right arrow basically point against each other. And here's how we're going to show that. Here we go. So there's my first arrow, and I'm going to call this the start. And so my electrons started here, and they got pulled in this direction. So now they're here. This end point for the first arrow is going to be the starting point for the second arrow. And so now they get pulled in this direction, and they're back over here where they started. Since I started and ended in the same spot right here, the result is nonpolar. And so let's show that again, just so we can see it. So I'm going to erase everything. Here's the first arrow. Here's my starting point. My electrons move in the direction of the arrow. That's where my second arrow starts, so I'm going to put its end right at this part, and I move back. I'm now at the Same spot that I started at initially. So overall, no electron shift has occurred. Let's look at another example. Here I have two molecules where I have a sulfur and some oxygens, and I have hydrogen and some oxygens. I have already drawn in the arrows for each of these bonds. And what we're going to see is that for this top example, when I move the arrows, here they go. There's the first one. Here comes the second one. And here comes the third one. Where did I end up relative to where I started? Remember, I started right here, and so I can animate that again if you want to see that. So there's my starting point. Where did the electrons get moved to? Since they ended up back where they started, the total sum of the polarity is nothing. And this molecule is nonpolar. But with water, you're going to notice something different happens. Both of these arrows are pointing up, but what's pointing down to cancel them? Well, it turns out the answer to that is nothing. Here's where I start. Oops. Here's where I started. Did I end where I started? I didn't. So that's like my electrons went in this direction instead. So here's what it's like my electrons did. So what that means is that my molecule has the electrons moving in this direction. They're on the side near the O and less on the side with the H. So this molecule is polar. And so your task will be to draw molecules, then draw their polarity arrows, and then try and consider how they add together. Now, obviously, moving arrows around on your pad of paper is not something that's easy to do, but you can use your fingers and try and approximate them. So like, oh, this arrow is this long, so I'll draw it over here and use your fingers as a spacer. And then I'll draw this arrow over here, and then I'll draw this arrow. And if you get roughly where you started, the molecule is nonpolar. But if you're displaced a lot and the arrows very obviously don't cancel, the molecule is polar. All right. Now, if you draw your Lewis structure poorly, you can actually get the wrong answer. For instance, drawing that SO2, if I had drawn it like this instead, or I'm sorry, the SO3, if I drew it like this, then my arrows wouldn't cancel out and I'd get the wrong answer. So it's very important that we use what we talked about with geometry to draw the correct Lewis structure. Are there patterns with the geometry of the molecule? It turns out that there are. Oops, I hit the wrong button here. And those patterns are going to be things like, do you have electron pairs? Because we don't do anything with the electron pairs. So for example, with ammonia here, here's what ammonia would look like if I drew it as a tetrahedron. And if I do all of the arrows, you'll notice that there's really nothing pointing down. So the end result is that everything's just going to go this way. And the reason for that is because of these arrows here, or this electron pair here. The electron pairs don't do anything with polarity. We ignore them. However, if I had a different molecule that was tetrahedral, such as this molecule, and I look at all these guys, you would again say that, oh, okay, these three bonds right here kind of have this result. They all sort of go up. But then I have this last one that goes down that cancels it. And when you get to 3 dimensions, it gets really challenging. I did have a few slides at one point that had this in 3D, and I tried to do the best I can, and it still looks really weird. But we do have some summary rules that we can make. And so that is, if an electron pair is on the central atom, then what ends up happening is that we lose the symmetry for our molecule, and the result will end up being polar. So the question is asked, just one H going down would cancel all three of them going up. And the answer to that is yes, but the reason for that is because this guy is going straight down, but these guys are only going sort of up. And I feel like the best way that I have to show you that would be if I opened up the PHET simulator right here. So let me get that on the screen really quickly. Hold on. All right, so let me make this guy right here. And I'm going to try and orient it so that it is as flat as possible. Okay, so that should work. That's not a web browser. That's my timer. That's what I want. Okay. Boop. There we go. So here is my molecule. And what you'll see is that these guys right here... Oh, my cursor isn't on this screen. Oh, there we go. Okay. These three right here. So there's one in the back, there's one in the front here, and there's one on the side. They are going up, but they're only going up slightly. This guy up here is going down completely. And it turns out that all three of these up components, these partial up components, add up to be exactly the opposite of this single down component. Now, if I take my molecule and I rotate it like this, and I put this in the back, now it looks like it's trigonal planar, and I would have the same situation with that triangle that I did before, where everything is pulling in one direction and then they all cancel out anyway. So the real trick to look for here is symmetry. If you have complete symmetry, your molecule will be nonpolar. And if you have the same four atoms connected to a tetrahedron, you have complete symmetry. But if I have this instead, remember that electron pairs don't count, so boop. Oops, there we go. Do I have complete symmetry? Let me try and get it back to how it was. Now I just have stuff that's kind of pointing upward, but I don't have anything pointing down to cancel it. So this molecule shown, and I clicked on the wrong part of it, so now it's going to go all over the place. It's really hard to get these back to how they were. This molecule as shown would be polar, because the electrons would either go up towards the middle, because they all have an up part, or if the electron density was actually pointing outside, then they'd all be going slightly down. Even though, if I rotate it this way, it looks like everything cancels out, but because they're not all in the same plane, there is some up or down component to it. So this isn't easy to do. I'm not going to sit here and say, oh, polarity is easy, just cancel the arrows. This is something that takes a second to get your head around. And there are patterns to do it. And so those patterns I put on the slide here, or I was starting to write them anyway. Okay, cool, yeah. So the 3D structure is super useful for this. And remember, let me give you the link again. I don't actually know if this is the right link. PHET. Yeah, here we go. Okay, so I put a dot on the end of that. Hopefully it still works. It did, okay. So that's the link again, and that link is also in the lab number 3 to help you, so you just play around with it. Because I think that it's super useful to just kind of bend the molecule around and see, oh, this isn't flat. If this were actually a live person lecture, what we would do is I would have model kits and I'd give them to you and you could build the molecule. And that helps a lot too. Unfortunately, due to COVID, we can't leave and do that. So this is the next best thing that I could come up with. So hopefully that is adequate. Okay, so if you have an electron pair on the central atom for our class, you're going to have a polar molecule. If you have different atoms along the outside, and it's not symmetrical, as a result, then what you end up with is polar. The exam is 1 through 5, so this is on the exam. However, I'm only going to ask you polar or nonpolar. I'm not going to ask you to draw a picture. I'm not going to ask you to draw the arrows. So if you absolutely just like, oh, polarity, I don't get it, just guess. Guess polar and nonpolar. And use these patterns. Oh, there's an electron pair. I'm going to guess polar. And 99% of the time, it'll be right. If a molecule looks to you like it's completely symmetrical, the answer is nonpolar. All right. I do have to clear this out because the text is going to appear right on top of it. We already did ammonia, and we just said that it's polar. And the answer is polar. It should say right there. But what I want to do is I want to put the homework practice up for sure. And what I want you to try and do, I'm going to give you a few minutes to do this, and then we'll go over the answers and then take a break. I want you to draw these molecules as best as you can. Again, geometry is really important. And then I want you to tell me polar or nonpolar. Now, up here it says draw polarity arrows, and again, you do not have to do that on a test. But for the purposes of you learning this, drawing the polarity arrows will help you. Okay? So these 4 molecules, try to draw their Lewis structure. I have a hint for the second one that the 2 C's are connected. So your molecule has to have this going on in your Lewis structure and something else. There may be more bonds here. There might be a double or a triple bond, but this is where you should start. Okay? I'll give you 5 or 6 minutes to try and draw these. And when we go back, we'll go over the answers. How are we doing? Do we need more time? I don't want to rush y'all. I have things on my screen that are blinking, and I don't know why. I gotta get to this screen. Let's erase. Let's see here. Oh, that works just fine. Okay. So let's go over the answers. So I gotta draw PCl3, and I'm, oops. Oh, that did work. Okay. I'm gonna just draw the Lewis structure, although I need more space, I think. And even though these electron pairs on the outside don't matter, I'm going to draw them in there just to be correct. So here's PCl3. And if I draw my arrows apparently. Oops, hold on. I have a mistake. So I got to look at the electronegativity table first to see which direction the arrows go. And I already know that Cl is more electronegative than P. So what I would draw is I would draw the arrows going in this direction instead. Now remember, if I were to like make this look in 3D, it'd look kind of like this. So there's my pyramid, and then here's Cl, P. That's not a P. What's wrong with you? And so if my arrows are all pointing away from it, they're still pointing down towards the floor of my little pyramid here. In other words, the molecule that we have, and I got to get the molecule generator back on the screen here. If you're getting a blurry screen, try toggling the setting to change the resolution. Because that does happen from time to time. Different people's internets. Oops, that's not the one I want. There you go. So the molecule that we just drew is like this guy. And that's still the wrong window. There we go. Oh, I gotta turn it on. There we go. So it's this guy again. And so instead our arrows are pointing outward, but also in the down direction. We don't have anything on the top because, again, these electron pairs don't influence our polarity. So this molecule is polar. So PCl3 is polar. And I'm using the eraser again. All right, let's draw CS2, which ends up looking like this. And if I compute the electronegativity between C and S, those numbers turn out to be really tiny, the difference between them. In fact, I got to look this up again real quick. So we're in chapter 5. Give me just a second. I think S is 2.4 and C is 2.4, right? They're both 2.5. Okay, cool. Sure, just a second. 2.5, 2.5. Delta En for this is 0. So there is no arrow to draw. And we just say nonpolar. So explain again how we know where the arrows are going up or down. Okay, so do you mean why I drew it in this direction and not, say, this direction? Sorry, I'm using arrows to indicate arrows and then drawing more arrows. It's not the best way to do it, unfortunately. But so the reason that I pointed these arrows from P to Cl is because if I look at the electronegativity table, I see that P is 2.1. So this guy is 2.1. And Cl is 3.0. So delta En is 0.9, which means that I point from the bigger one, or I point towards the bigger one, which is Cl. So my arrows are all going that way. Now, remember, for the purposes of our class, you only have to tell me it's polar. You don't have to tell me which direction. So even though you pointed it in the wrong way, if this were a more advanced class, then you'd lose half a point or whatever. But for our purposes, you just have to say polar yes or no. And so you'd be correct. So why are we drawing CS2 as a line? So that is from earlier in chapter 5. Let me erase this to get it out of the way. To draw the geometry of the molecule correctly, we would count its electron groups. There are 2 electron groups. And so its Vesper geometry would be linear. And you're probably going, oh shoot, I have to know all of these things together. And yeah, you do. Everything builds on itself in chapter 5. It's sort of a mess and I hate it. And it's totally okay to get lost or confused for a second. Because I am throwing a ton of information at you. And the good news is we're almost done. There's very little left that we have to do. I don't know why I'm doing this way. Ooh, that's not what I want. That's what I want. Alright. Is this gonna... Okay. Oh, wait a second. It's not gonna... Oh, darn it. Okay, hold on. I had a cursor selected and it wasn't showing me that. Alright, what's my next molecule? Alright, this is the challenging molecule, so hopefully you drew... Oh, I'm all the way over there. Hold on. I flipped the pen over again and it got mad at me. So I told you had to start with this. And so... Oh my goodness, why is everything the worst? Hold on. Select none. Alright, everything works. Great. Photoshop! There we go. So, I'm going to put my CLs like this. I'm going to put 2 on each side to make my molecule as symmetrical as possible. And then the last thing that you would end up having or seeing is that if you had 2 electrons left over, you'd put them here, and then you would immediately just move them into the double bond so that both things have an octet. And so this is trigonal planar. This is trigonal planar. There's totally 2 CLs. I'm doing the wrong molecule. Whoops. None of that happened. Oops, that's also not what I want. Sorry, you're totally right. Where's my oops sound effect for when I make a mistake? Here it is. Oh, you can't hear it because I have the sound muted. Hold on. Alright. Tell him what Wes has won. A big fat oops. Yeah, I apologize for that. Let's do the correct molecule. That's not even the pen. Oh, I'm a mess. There we go. So we'll start here. We're going to put a CL on each side. And the end result that you'll see is that this is what you have to do. This molecule is linear because we have 2 electron groups on the left and also 2 electron groups on the right. So this whole thing is in a line. Here's my electronegativity numbers. So that means I'm going to go like this and like that. And you can see that these cancel each other out because they're pulling in opposite directions. So this one's nonpolar also. Oh, I ran out of space. Hold on. For the last one here, I'm going to put the H's on the bottom here. We'll put Cl on top. Remember that part where I said if you don't have all the same atoms around it? Well, guess what? I don't have all the same atoms around it. I have a bunch of H's in the Cl. So automatically, it's polar. But let's show why that is using numbers. So all these H's are going to point inward. But then this Cl bond is also going to point up. So you can see that my electrons are sort of just doing this thing, right? So normally we would need like a down part to cancel down the stuff at the bottom. But I don't have that. I have it pointing in the other direction. So everything just points up here. So all the electrons go whoosh, and they get sucked up here towards Cl. So follow the arrows, they show you where to go. But if you can look at these with geometry, then you're all set. How did you decide that C was the central atom? Do you mean specifically in CH3Cl? Or did you mean C2Cl2? Sorry. Or did you mean CS2? I have all these C's on the board. Yes, all of them. The first atom that is listed is the central atom. As long as it is not H. So since I wrote CH3Cl, that first C has to go in the middle, and everything else goes on the outside. All right, any other questions? How do we know when we go in a line? So you have linear stuff when you have two electron groups around a central atom. So if this is my central atom, there's two electron groups, which is linear. And I got to get another color here because I'm working in the... Now for this central atom right here, I also have two electron groups. And that's also linear. And if things are all linear, they just all line up in a row. So as long as I keep having central atoms that are linear, everything will be linear together. Other questions? Yeah, you got it. Actually, you know what we should do, since we're due for our break anyway. What I'm going to do is I'm going to put the break timer up. And if you have questions, I'll let you just post them in the chat during the break. So let's start our break. I'll turn the music back on, and I'll see you in a bit. Oh, I was so close. One of these days I'm going to stop it exactly on 10 minutes, and it's going to be wonderful. Where am I? I am turning this guy off. I put the nighttime theme up because everyone's like, oh, it's so difficult. I'm like, well, I guess it's time for the gloomy Everett pictures. It's just Everett at night. Or EVCC, actually. I want to do this one. This is the last thing we're going to do today. There's 5 slides, and it's how to name stuff, and this is actually probably one of the easiest things you've done in this class. So we're going to round out Chapter 5 with something that's much, much easier. Now, the difficult part of this is actually not getting these naming rules mixed up with the ionic rules. So, in Chapter 4, you learned how to name stuff. And hopefully you've had enough time to understand how to name an ionic compound, what the Roman numerals are for, how to put the polyatomic ions in there, etc. In Chapter 5, we're going to name covalent compounds. And remember, covalent compounds don't have metals. They don't have ions. They don't have polyatomic ions. So, you don't have to learn any of the things from Chapter 4 to do this part. You just have to follow this rule. So, to name a covalent compound, we're going to name substances that only have 2 elements in them. And of those 2, one's going to come first and one's going to go second. The general rule of which element comes first in a covalent compound is that the one that's the most metallic, in quotes, goes first. And you'll remember in Chapter 3 that the elements can be sorted by whether they're metal or non-metal, and that if you go towards the left, you get towards more metal. So we're going to put elements that are further to the left before elements that are further to the right. I have this on the screen here, and the only one of these that I really care about is this first one. And these other ones are just never going to come up. So this one especially down here, just don't even worry about this one. In fact, I wouldn't even worry about this one either. Sometimes you will see H going first. So like H2O, or HCl, or maybe some other ways. That is written that way because of a specific property of how H works. And we're going to talk about that in Chapter 10. It's called acids. And in some substances, the H acts like it is acidic when you combine it specifically with these elements. So, for the most part, you're not really going to need to worry about the order in which the elements goes. I'm going to just give you something like CO2, tell me its name, or I'll tell you carbon monoxide, give me its formula, and you'll have to do that. So don't worry too much about this slide. When we name... I seem to be missing a slide. Where is... I wonder if that got deleted on accident. Okay. What I'm going to do is I'm going to go to here real quick. Give me just a second here. I was expecting a slide to appear, but it didn't. Okay. So I'll just leave this here for now. Let's delete everything on the screen. Alright. So to name covalent compounds... you're going to use an algorithm, and the algorithm is the following. So in the first box, just like before when we're just dropping names in the box, you're going to name the first nonmetal. And for the second element, you're going to name the second nonmetal with "-ide". And you might be looking at this and saying, how is this different? And this is how it's different. There is one extra thing that we have to do. In each of these boxes with the purple pound symbol, or the hashtag, I guess is what the cool kids call it today, we're going to put in what's called a numeric prefix. And you've probably heard of these prefixes before. That was supposed to be a tetra, but I kind of wrote on top of itself. And so these are in your textbook. Oops, I forgot to put hyphens after these. Put the hyphens in the wrong spot. That's what I was doing. These are in your textbook in Table 5.1. And so what you're going to do is whenever you have a certain number of an element, you're just going to stick this prefix in the purple box. So, for example, if my compound that I gave you was this, and I said name this, well, you would name the first metal, or non-metal, which is nitrogen. And you'd name the second non-metal with "ide." And then you attach numeric prefixes. I have 2 nitrogens, so I use the prefix 2. And I have 5 oxygens, so I would use the prefix for 5. And then, as a convenience thing to make it sound better, there's going to be some spelling things. So I just erased this A on here to make it sound better. You're going to see these in a second, so you don't have to worry about them. But knowing the numeric prefixes is all you need to add to your repertoire to be able to name any covalent compound. And so this naming scheme is what we're going to follow to name all of these. All right. Now, of course, there are exceptions, because where would we be if there weren't exceptions? Here are the exceptions. So one of them is the spelling thing. There is a second exception. On the first element, if there's only one, you don't say mono. So, for example, if I had this... Oops, that's the wrong pen. So let's just do this. If I had this substance, we would follow the same rules. And then there's one of each, so I would say mono-nitrogen monoxide. But I don't put mono for the first element. And so this is the proper name, nitrogen monoxide. If you end up with a weird spelling combination where you get this combination, where you get an A and an O together, the way that we fix it is we delete the last letter on the prefix to get pentoxide. This also happens if you get 2 O's together. We don't go monoxide, we just get rid of this O here, and you say monoxide. That is a deleted character and not a space. And then finally, never, never, never Roman numerals in covalent compounds. So you should never have a Roman numeral because you never are counting the charge on something. Covalent compounds don't have charges, so they don't get Roman numerals. So let's go over some examples. And you'll see that this is actually pretty straightforward. Of course, I pick the one example that I already had. Let's do this one instead. I hate when I do that. So what would I call CO2? So I'm going to name them in this direction here. So first, name the first one. C is carbon. Next, name the second one. That's oxygen with an ide is oxide. And then attach the numeric prefixes. The first one has 1. We don't put mono in front of the first one. But the second one has 2. We would say that. And you have heard that name plenty before, carbon dioxide. How about this one? Not allowed to call it water anymore. You have to call it by its proper chemical name. You can call it water all you want, I don't care. But we'll do the same thing. What is this element called? It's called hydrogen. What is this element called with ide? Oxide. And it is carbon dioxide. Good. Now I have to go in and fill in the prefixes. I got 2 of these, so I'd go 2 for hydrogen, dihydrogen. I have 1 oxygen, so I'd go monoxide. And there's its name. Now that's silly. Why do I have to call it dihydrogen monoxide? Everybody knows what water is, right? Well, not everybody knows what dihydrogen monoxide is. And with all the fake info and fake news going on in the world today, I thought I would give you some fake news of my own. And these are things that have actually happened in the world. They're not fake news. These are actually events, but they are events centering around fake news. For instance, a while ago, this petition was circling around in various places. And this is a real thing that happened. It was actually a joke in one country. They brought it up in the Senate for April Fool's Day and made motions to vote on banning this, and it was actually to raise science awareness, and then everybody went haha and chuckled. The second country talked about this on a radio show and said, there's dihydrogen monoxide in all of our water sources. This could be really bad. And then they listed these facts. So keep this in mind. Country 1, Senate moves to ban this on April Fool's Day, and they all talk and laugh, and it's to promote science awareness. Country 2, radio show talks about this, mass panic and paranoia. Which country, country 1 or country 2, was Australia? And which country, country 1 or country 2, was America? Type your answers in the chat now, and we'll see if you know who the idiots are. Disclaimer, I am half Canadian, and I am claiming to be full Canadian for this question. Yeah, surprising absolutely nobody. This was a radio station, and I believe it was in Atlanta, Georgia. And they got pulled off the air real quick. So, like, after an hour, they had thousands of people calling in. I heard about dihydrogen monoxide in my drinking water. That's gonna be bad for my kids. Rah, 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 rah. And so, the whole point of nomenclature is that this is a scientific system that exists, and people are going to use that to take advantage of you. Because the facts that I'm going to share with you about dihydrogen monoxide are terrifying and revolting, and they might make you cringe and regret all sorts of things. First of all, dihydrogen monoxide, another name for it is called hydroxyl acid. It is the major source, or the major component, in acid rain. Just in case you didn't know that, almost all of acid rain is dihydrogen monoxide, and that's pretty scary. Did you know dihydrogen monoxide contributes to the greenhouse effect? It's even a more severe contributor than CO2. I mean, we talk all about CO2 and curbing emissions and carbon tax, but dihydrogen monoxide is even worse at doing this. If you are exposed to dihydrogen monoxide under certain conditions, you may get severe burns, and if you breathe it, you will die. No kidding. If you breathe dihydrogen monoxide in, game over. Not only that, it contributes to erosion. It will deteriorate our wonderful landscape. It rusts metals and it corrodes them. It could ruin your automobile's brakes, and it may cause electrical failure. Every single person who has cancer in America and worldwide has this chemical in them. I kid you not. Every single person. And yet, despite all of these terrible things that dihydrogen monoxide has been found in and around, we still use it to this day. And here are things that we use it for, and this is just terrible. We use it as an industrial solvent and coolant. You use it in nuclear power plants. Do you want nuclear power plants to be contaminating your acid rain? We use it to make styrofoam. It's used as a fire retardant. It's used in animal research. It's used in pesticide. Even if you wash your vegetables, your produce still has it on them. It's used in junk food. And you know what's great about all of this? It's fucking water. It's water. But if you did not know that, and you saw this list of facts, you might be considering, like, whoa, holy crap, this is awful. Because clearly the tone of this is meant to get you sympathetic to, Jesus, this is out there? I don't want this anywhere near me. And yet you totally do want it near you because it's water. You need water. I've heard of the plate tectonics one. Another one that I saw that was popular was somebody went around asking people to ban women's suffrage. And hundreds of women were signing this petition to end their right to vote, saying, I don't want women to suffer, because they didn't know what that meant. So the whole point of this little, 5-minute slide was that there is a lot of technical mumbo-jumbo and jargon out there that is meant to manipulate you. You've probably heard people petitioning, I don't want anything with chemicals in it. I don't want to eat any food with chemicals. And what I say to that is, well, I hope you enjoy starving because food is chemicals. Everything is chemicals. That's just what the definition is. And so what's important is that you expand the amount of knowledge that you have and then learn where these pitfalls are so that people can't take advantage of you. Because if you sign away water, that's absurd. And there are people out there that will try and do that to take advantage of you. All right. There is a website for DHMO, but in the interest of time, I'm just going to go straight to the examples. I want you to try and name these compounds using the naming rules. And then once you have named some compounds, you got to go in the opposite direction. Write the formula for these names. There's the homework practice at the bottom. I'll give you 5 minutes to get all the names down, and then we'll go over the answers and we'll call it a day. There's so many questions, I'm just going to answer them in voice. I was typing these out. I was like, oh crap, I fell behind. So, there's not a practice exam, but you do get 2 attempts at the exam. So, the first time you do it, you'll get to see what your score is, and that's it. But you can try again. There is a study guide. If you go to the modules page, let me actually get that up here real quick. So if you go to the modules, excuse me, and I actually revealed it. This wasn't revealed before. It's right here, Chem 121 Exam Study Guide Topics, and it's just a list of all the topics we've covered in this class. Yeah, that's pretty much it. So it's just those. That's chapters 1 through 5. I've distilled it down to 1 page. Let's see here. I am going to talk about some stuff on the exam at the end of the lecture. Let's go over the answers first, and then we'll talk about that. There's my pen. I got to get back onto that screen. All right, so let's name these. So there's 2 nitrogens, so I'll go dinitrogen. And then there's 1 oxygen, so monoxide. 2 chlorine is dichlorine. Sorry, I had a spelling fart there. Trioxide. We got 1 sulfur. We don't put mono on the first one, so sulfur, hexafluoride. And then for P4O10, we have 4 phosphorus, so tetraphosphorus. And then deca oxide, so it's decoxide. There you go. And then this last one's pretty easy because it's like, okay, what's boron? There's 2 of them because it's di. What's oxygen? There's 3 of them. And so you can just really quickly whip those out based on what the name tells you. And you'll have to do both on the quiz and the exam. So hopefully you did all right on that. Nice way to round at the end of the lecture so that we do all the hard stuff and then I end with something easy. So it's like, okay, I can do this again. Just take a deep breath, and you're going to be okay. In fact, at this point, you are now 50% of the way done with this class. Can you believe it that we're halfway done? I sure can't because I'm drowning in like stuff to prepare for you guys, just like you guys are probably drowning in studying. But we'll make it. We'll make it through. So hang in there. Any questions on naming covalent compounds before I talk about the exam? All right. I believe the next slide is celebrate. Hooray. You didn't get to hear the sound effect because I had it muted, so hold on. There you go. And again, hooray, 50% done. So you're halfway there. Don't give up yet. But what we're going to do is I'm going to put this on here. My poor orc up here. This is my World of Warcraft at work when I played World of Warcraft like years ago. Like 15 years ago. Oh my goodness. Maybe not that long ago. No, maybe it was that long ago. Okay. So let's talk about the exam. So the first thing to note is that you can't see anything because I am behind my orc. So there we go. The first thing to note is when is the exam. So the exam is open on Monday. What date is Monday? Friday, Saturday, Sunday, Monday, which is the 18th. And it opens at midnight. And it closes at 11:59 p.m. So it is only available on Monday. Okay? You have to take the exam at some point during Monday. And I believe that the time limit for you guys is 120 minutes. So you get 2 hours to complete the exam per attempt. So you're going to need 4 hours of total time set aside to do the exam that day. When will lab worksheet number 2 be graded? I really hope I can do it tonight. It is the next thing on my list to do. I've been behind because I've been writing all these lab worksheets and stuff, and then grading, unfortunately, is the lowest priority. Yes, I keep the better of the 2 scores if you take the exam twice. So if you got a 70 the first time and an 85 the next time, your score is 85. Now, there are some caveats to this. So the exam closes at 11:59. If you start the exam at 11 o'clock, I don't know what happens. I don't know if it lets you keep going on whatever your attempt you're on. I don't know if it will close you mid-exam or if it just will stop and disappear after you're done. Just like the quizzes, it will show you your score. Show score after attempt. And so it'll tell you, hey, this was your score. And so you can use that information to say, oh, okay, I want to do it again. Or I'm very happy with that and I'll move on. There will not be a key posted for the exam. So what that means is that that screen that you see is all you will ever get for exam 1. Okay? The reason for that is because I need to keep my exam to be able to use it again. And if I post the key, this is scrolling behind my thing. If I post the key, the exam is compromised more or less, and then that's no good because the key is out there. So there will not be a key. I will not be unlocking the answers. You will only ever know your score on the exam. Now, other caveats about the quiz. Is that it's going to put one question at a time on the screen, and you cannot return to previous questions. Okay? So what that means is you're going to have a question on the screen, and if you don't know the answer, select something and move on. You will have to simply just continue. Okay? If you don't, you will time out. You will run out of time. Now, that's obviously not great. That's the bad news. But the good news is there are 83 points possible, but only 75 are graded. So what that means is 8 of those points are extra credit. So if you get to 1 or 2 questions, you're like, shit, I don't know the answer to that, I'll just guess. That's fine. You do not need to get a perfect score to get 100%. In fact, if you get a perfect score, you get 110.6%, or whatever it works out to be. Okay? So yes, the exam is a little harder, and the reason for that is because I need an accurate assessment of what you know. Okay? Now, I don't know what your studying and resources are in this class. In my other class, I know there's a Discord server where everybody is talking to each other, and I know that everybody talks to each other about the quiz when they're taking it because you have a week to do it, and that's fine. You talk to each other about the quiz and stuff. The reason that I have this on such a tight constraint is because I want to minimize that. I can't prevent it. I'm not going to try to prevent it and make you use the honor lock system where you're looking at the screen and it's recording you. I think that's bullshit. But what I do want you to do is I am going to put a more severe constraint on you to see if you know the material. Okay? And so this is the method that I'm going to use. Now, that does mean there's a lot of pressure, but if you've been working on the study guide and doing the problems all along, you should be in a decent shape, okay? Remember, you don't got to get everything right. Don't panic about it, okay? Oh, that was the other thing I wanted to say. So the breakdown of the questions is going to be, there's going to be 15 or so multiple choice. And it's only going to be multiple choice, so it's going to be you just choose A, B, C, D. And those are each worth 2 points. So 30 points. And then the remaining points, which is like, what, 53 points, are going to be other questions. And those questions are going to be very similar to what you've seen on the quizzes. In fact, they may be the exact same quiz questions with just different numbers. Okay? So if you've done well on the quizzes, then you'll be okay. And in fact, if you want to prepare for something, go look at all the quiz questions that you've taken and look at the answers and just do the question again and see if you can get the same answer. Or maybe change the numbers on your own and see if you get a similar answer. Or something like that. Okay? That's going to be exam 1. It will be on Monday. You will get an email that says it is now open. And then you have 24 hours to take it once or twice. And then I will have all your scores the next day, and I will put them in the gradebook. Okay? Between now and Monday, if you have any questions, you gotta email me, okay? Because this is the last chance you have to email me. I cannot answer questions for you during the exam. And so all day Monday, I will not be able to answer student questions. Okay? I'm going to put the title card back up. That's it for today's lecture. The exam covers chapters 1 through 5. And it will be on Monday. So make sure that you have some time set aside to do it. Have a good weekend. Stay safe, stay healthy, stay home, and best of luck on the exam. We're all counting on you.